This is the video for pre-lecture 18. So up to this point we have been introducing numerical methods for solving ordinary differential equations. We started with the initial value problem, then we continued on to the boundary value problem, and now we're going to combine the two approaches to solve partial differential equations. So a partial differential equation is a differential equation of some quantity or quantities that depend on two or more independent variables. So we have a couple of examples here. It can be a function of both space and time, a function of multiple dimensions in space, or a function of multiple dimensions of space and time. For this class, we're going to restrict ourselves to problems where we have one dimension in space and time. So we use the time marching methods to advance in time our matrix or boundary value problem methods to solve for spatial dependence at each time step. So we've previously discussed the idea of a well-posed versus an ill-posed problem, but effectively for our class we're primarily going to be focused on only well-posed problems which provide a unique solution to our ordinary differential equation with results that sort of smoothly vary as a function of our boundary conditions. There are some other ill-posed problems that are certainly of interest, but we're not going to focus on those in this course. So, 3 example PDE systems that we're going to be looking at in this course. So, the first system is called the advection equation. And the advection equation is just simply d phi dt is equal to minus c d phi dx, where c is some sort of wave speed. And this actually has an analytic solution, which is that given an initial condition phi naught at time t equals to 0, the analytic solution is just simply phi as a function of x and t is equal to phi naught using the variable combination x minus ct. So effectively this allows our solution to just simply be a translating wave at a given wave speed. So this needs one boundary condition, it also needs an initial condition, and some wave speed c, which can possibly be variable, but as often for our purposes, constant. So this is a system which does conserve energy. The next system is the diffusion equation, or the heat equation. So this is d phi dt is equal to kappa d squared phi dx squared. So we need an initial condition. In this case, we'll need 2 boundary conditions, and kappa is our diffusion coefficient. And we can see for this example, we have our signal at the bottom, which smoothly deforms down to an average temperature value of 0, eliminating those gradients quite quickly. And if we have both the diffusion and advection terms, so this would be d phi dt plus c d phi dx, so we pull that advection term to the left-hand side, is equal to kappa d squared phi dx squared. This is our diffusion advection equation, and so here we can see our solution is slowly smoothing out, but also advecting at some given wave speed. And what you'll notice is that there are a lot of terms here that look very similar to the Navier-Stokes problem. There's this time derivative, this advection term where we have a velocity times spatial gradients of first derivative spatial gradients of our quantity of interest, and then second derivatives times some sort of diffusion coefficient. Really the only thing we're missing is maybe that pressure term, which could be sort of analogous to a source term. Okay, let's take a look at the first equation of interest, which is the advection equation. So the advection equation has an analytic solution, as we just said, and that analytic solution can conserve the discontinuities that we might have in our system. And so if we have an initial step function, like what we see here on the left, an analytic solution would just simply take this solution and propagate it to the right or the left at some constant speed c. So to solve this numerically, we have to do a couple things. We have to first select what time marching scheme we're going to use, and then what spatial discretization method we're going to provide for our boundary value problem. So we can use an explicit or an implicit Euler method. This would provide us an order delta t approach. Obviously, if we use the Runge cutout, Crank-Nicholson, or some higher order schemes, we can get a more accurate time marching scheme, but this comes at a slight cost numerically. Then we can have a forward or backward approximation of our spatial derivatives, or a central space discretization that would provide us an order delta x squared approximation. one of the big shifts that we're going to make is we're going to be using both subscripts and superscripts for our index. So for our time index, n, we're going to, from now on, you label these as a superscript. So they're going to go slightly up relative to our variable. For our spatial indexing, I, we're going to have these slightly depressed as our subscript. So that's just a point of reference for us. So let's talk about the advection equation. So we want to create the finite difference equation using an explicit Euler central space approximation. So let's start off by just writing our explicit Euler equation. So our explicit Euler equation was phi at time index n plus 1 is equal to phi at time index n plus delta t times d phi dt. And we're going to evaluate this all at the spatial index I. So it's going to be I here, and I here. Okay? And now, if it's an explicit Euler scheme, then we're also going to evaluate our time derivative at some time index. And if it's explicit, we're going to evaluate that at time index n. So now we have to make a substitution. So this d phi dt goes in here, which means we can make the substitution that phi I n plus 1 is equal to phi I n plus delta t times minus c d phi dx evaluated at time index, or spatial index I and time index n. So now we've converted our time derivative into a spatial derivative, and we have to discretize that spatial derivative using some finite difference approximation. In this case, we're going to make a centered space approximation. So we again have phi I n plus 1 is equal to phi I n plus delta t times minus c. And now we have our approximation for d phi dx. If it's a centered approximation, this is going to be phi I plus 1 minus phi I minus 1 divided by 2 delta x. And for both of these, we're going to evaluate them at time index n. So that allows us to match our time index here and here. So notice, as we're taking the spatial derivative, we're holding our time index constant. Okay? So we can rearrange this equation slightly, and gives us something like phi I n plus 1 is equal to c delta t over 2 delta x phi I minus 1 n plus 1 minus c delta t over 2 delta x times phi I n. So, critically, we're going to assume that we know our current state. So the current state which we'll label as our phi n vector, meaning that we know the value at all spatial positions at our current time index n. This is known. Our next state at time index n plus 1 is unknown. This is what we're trying to solve for. Okay, so our knowns are on the right-hand side, and our unknown, we have only one, and it's on the left-hand side. And so this is nice because what this means is we can take all of the known information, plug it into this simple equation to determine what our unknown state at time index n plus 1 is. Well, so this was using an explicit Euler scheme, so we should assume to some extent that this would be the case given our experience with the explicit Euler scheme for just purely time marching. Well, what happens if we use an implicit method? Well, if we use an implicit method, Then our equation is, for our base equation, is phi n plus 1 is equal to phi n plus delta t times d phi dt evaluated at time index n plus 1. Okay, well, what are the ramifications for that? Well, now our spatial derivative is evaluated at time index n plus 1, which means so should our substitution-ins for our finite difference equation. Now this has the following ramification. Now we have a little bit more difficulty combining these things, so we'll maybe label this properly as the explicit Euler equation. For our implicit Euler equation, we're going to have an interesting combination of unknowns. We're going to have our phi I n plus 1 is equal to phi I n minus c times delta t over 2 delta x times phi I plus 1 n plus 1 plus c delta t over 2 delta x times phi I minus 1 n plus 1. Now if I highlight my unknowns, what you'll see is I have 1, 2, 3 unknowns at my state n plus 1, and only one known at my state time index n. Well, fortunately, we have one of these equations for each of our positions in space and a couple of equations for our boundary conditions as well. So we'll have a system of equations. But you can see now using the implicit Euler scheme is going to add a degree of complication. The final thing I want to discuss is the idea of a stencil. And so a stencil is sort of a visual representation of what nodes are being used for a particular scheme. So we just looked at the explicit and implicit Euler methods and applied a centered space approximation. So for the explicit Euler scheme, what terms do we use? Well, we used our phi n, For the explicit scheme, at least, we used phi I plus 1 and phi I minus 1n, as well as phi I n plus 1. So we used the following 4 elements. Okay. For the implicit scheme, we used phi I minus 1n plus 1, phi I n plus 1, and phi I plus 1 n plus 1, as well as phi n. And so if we were to draw the boundary of our stencil, we can see that this sort of looks like a Tetris piece here, and an inverted Tetris piece down here. So why might these be important? Well, again, if these are our knowns and these are our unknowns, it gives us an idea that some of these equations might be coupled. So for our implicit case, we see that we have a system of coupled equations because we have multiple unknowns showing up. Another interesting thing for us to visualize is what would happen if we were doing a different spatial discretization, if we were doing a backward space approximation, for instance. Well, our shape would look a little bit like this. Or, for the implicit case, would look something like this. And we'll talk on how the shapes of these stencils ultimately impact the way error propagates through our system.